Today, we're going to pull back the curtain on the magic that connects our entire world. We're going to deconstruct how modern networks actually work, from the moment you make a single click all the way to the automated cloud.
You know, it all really starts with the simple question. When you click on a link, what is actually happening behind the scenes? How does that little request navigate a maze of cables and devices, find a server that might be thousands of miles away, and bring back exactly what you wanted, all in the blink of an eye? So here's the game plan. We'll start with the basic language devices used to talk to each other. Then we'll see how we control that conversation. After that, we'll cover how to keep the whole system healthy, see how it all scales up, and finally, dive into the revolution that is network automation.
Okay, first things first. Before anything cool can happen, devices need a common language and a way to find each other. This is the absolute foundation for everything else we're going to talk about.
You know, at the very heart of it, applications have two main ways of communicating. First up, you've got TCP. Think of it like registered mail. It is meticulous. It makes sure every single piece of your email or that file you're downloading arrives perfectly and in the right order. But then you've got its wild cousin, UDP, the speed demon. It just blasts data out as fast as possible, perfect for video streaming or online gaming where a tiny momentary glitch is way better than a long, frustrating pause for buffering. So how does a device even get its identity on the network? I mean, can you imagine having to manually type in IP addresses for every phone, laptop, and smart TV? It would be a total nightmare. That's why DHCP is such a lifesaver. When a device joins the network, it basically just shouts out, "Hey, I'm new here. I need some network settings." And the DHCP server automatically hands it a unique IP address and everything else it needs to get online. Simple as that.
Okay, let's put these pieces together in a real-world scenario. You type a web address into your browser. The first thing your computer does is use DNS, which is basically the internet's phone book, to look up the real numerical IP address for that name. Once it has that number, it opens up a reliable TCP connection to the server and sends an HTTP request that pretty much just says, "Hey, can you please send me the contents of this web page?"
All right, so our devices are talking. That's great. But we probably don't want them talking to everyone about everything. So now let's look at how we build digital walls and set the rules of the road to control and secure all that traffic. The main tool for this job is something called an access control list, or an ACL. And look, if you only remember one thing about ACLs, make it this. They use first match logic. A router reads the list of rules from the top to the bottom, and the very first rule a packet of data matches is the only one that gets applied. That's it. Game over. Let's walk through an example, because this is super important. A packet comes in from the address 10.1.1.5. Now, you might look at this list and see rule number 2, which is specifically designed to deny that traffic. But watch what happens. The router starts at the top with rule 1. Rule 1 says permit anything from the 10.1.1 network. Since our packet matches that rule first, it gets permitted immediately. The router never even gets to rule 2. That's why the order of these rules is absolutely everything. And one more thing, at the very bottom, there's always an invisible deny all rule that blocks anything that wasn't explicitly allowed. Now, beyond just filtering traffic, we can lock down the physical network with this powerful trio of features. Think of it like a three-legged stool for security. First, port security stops some random person from plugging their laptop into an empty jack on the wall. Then, DHCP snooping stops a malicious actor from setting up a fake DHCP server to hijack your traffic. And finally, dynamic ARP inspection prevents an attacker from impersonating another device, like your router. Altogether, they form a really solid defense at the most basic level.
So we've built our network, we've secured it, but the job isn't over, not even close. Now comes the ongoing task of keeping it running smoothly. This part is all about the tools and protocols engineers use to monitor the health and activity of the entire system.
This next one might seem like a small detail, but trust me, it is absolutely vital. Time. Just imagine trying to figure out a security breach when every single device's clock is off by a few minutes or even hours. It would be total chaos. You'd have no idea what happened, in what order. That's where NTP comes in. It's the essential service that synchronizes every device to a single authoritative clock, which means that when you're digging through logs, you're looking at one accurate, trustworthy timeline of events.
Okay, so how do engineers figure out what's plugged into what without having to physically trace 1,000 different cables? Well, they use discovery protocols. For a long time, if you had Cisco gear, CDP was your go-to for mapping things out.
But today, the industry standard is LLDP, which does the exact same thing but for equipment from any manufacturer. It's a massive time saver for just understanding the physical layout of a modern network.
All right, let's zoom out a bit. How do we take all these concepts we've talked about and design networks that can scale from a single office building all the way up to a globally connected company that relies on cloud services? Well, it all comes down to architecture.
To build a big, reliable network that doesn't fall over, engineers often use this classic three-tier model. At the very bottom, you have the access layer. That's where your computer actually plugs in. Moving up, the distribution layer acts like a traffic collector, aggregating data from all those access points. And at the very top, you have the core layer, which is just a super fast backbone connecting everything together. This layered approach makes the network predictable, way easier to troubleshoot, and a whole lot simpler to expand when you need to.
But what about connecting an office in New York to one in London? There are a few key ways to do that. Metro Ethernet is kind of like stretching a really long Ethernet cable across a city. It's fast and simple. For more security, MPLS creates what feels like your own private network, even though it's running over a provider's shared equipment. But probably the most common approach these days is a simple internet VPN, which builds a secure encrypted tunnel right over the public internet. It offers a fantastic balance of cost and security.
And that brings us to our final and honestly most transformative section. Manually logging into hundreds of devices one by one is just slow, and it's practically begging for human error. The future, and really the present, is all about automation. It's about telling the network what you want it to do, not meticulously programming how to do it.
The whole revolutionary idea behind software-defined networking, or SDN, is this separation of the brain from the muscle. See, in old-school networks, every single device had its own brain and its own muscle, all bundled together. SDN takes the brain, the control plane, and pulls it out, centralizing it in a single piece of software called a controller. This controller gets this amazing bird's-eye view of the entire network and can then program the muscle, the data plan, on all the devices at once. It's a total game changer. Intent-based networking takes this idea a massive step further. Instead of writing a bunch of complex rules, you just declare your intent. You say something in plain English, like, I want to allow the web servers to talk to the database servers and no one else. The IBN controller then automatically figures out how to translate that business goal into the nitty-gritty network configuration across the whole system. It's pretty amazing.
And how does all this automation actually happen? Well, it happens through APIs that use simple data formats, like the JSON you see here. It might look a little technical, but it's just a text-based structure that's really easy for both humans to read and for programs to understand. Automation tools and controllers just pass these little text files back and forth to configure and monitor the network.
Now, to make sure all these automated configurations stay correct and don't drift over time, we use special tools. They mostly follow one of two models. You have the push model, where a central server, like Ansible, reaches out and actively pushes updates to all the devices, or you have the pull model, like with Puppet or Chef, where a little agent living on each device regularly checks in with a central server and pulls down its correct configuration. Two different philosophies, same end goal. And all of this brings us to our final thought. We've gone on this incredible journey from basic protocols all the way to intelligent, automated systems that understand intent. The whole industry is shifting away from manually typing commands on individual boxes to just defining what the business needs and letting software do the heavy lifting. So the really big question is this: as this transformation continues to accelerate, what are the skills that the network engineers of tomorrow are really going to need? Something to think about.